Okay, so today what I'll do is explain to you the duality theorem, the way it ends up working. Give you like at least a mini proof. I won't go into all the details. Like the book does like a good gives like a very good explanation for it if you want to know all of about it. But now that we have this like Farkas lemma, the proof is simple enough that at least I can tell you what's supposed to happen. Um, And then I'll give you some applications of the duality theorem, like some mathematical applications of it. And then next time, what I'll do next time is kind of like to give this application to game theory of the duality theorem, which is like kind of like fun. It's like a nice one. I already have like I already have created like a list of problems. I'll just add like maybe two or three more related to this, and then I'll post it tomorrow for you to have something to look at in the meantime. So let's see. Okay, so before I write the duality theorem, there's still something that's useful to understand about the Farkas lemma. Um, so again, what Farkas, to summarize, says is that Farkas lemma is that one of two things happens, right? So here you were looking at a system of equations which is ax equals b with x greater or equal to 0. Okay, so the two possibilities for this system are that either it has a solution or it doesn't, right? So if it doesn't have a solution, oh, sorry, option one is that there is a solution. And what that looked like is that the vector b was in the cone of the columns of A. So again, like just to kind of like draw the cone. So you had the cone here, and then B is part of the cone. So that's what it means to say geometrically that this system of this equation together with x being non-negative uh, having a solution means. Okay. Um, And option two was this separation condition, right? Which is like that you can separate if there's no solution to the system, right? Um, if there's no separation to the system, then you have the cone. Let me just copy it. The cone here. And then you have like the hyperplane that separates the vector, right? And here you have B. So this is like the hyperplane that separates the vector from the cone. So you have the cone here. And the plane has a normal vector, which for today, because I'm going to talk about the duality theorem, it is convenient to call the normal vector y. So I'll call it y. Oops. So this like is the normal vector to the hyperplane. And the condition that this is separated is that all the vectors inside the cone are kind of like at an acute angle with this one. So y dot a is greater or equal to 0 for A being any column of the matrix. And the and then the other condition is that the vector B is making like an obtuse angle with the normal vector. So y dot B is negative. Okay, so it's kind of like positive on the cone, the dot product is non-negative on the cone, and it's negative on the vector B. So those are like the two options. That okay? Is that making sense? So that's roughly what it says, and it's like a very nice geometric picture of what's happening. Now, if you remember, like many times, like when we start like the optimization problems, it's in inequality form. So it's also useful to understand what the version of this is if you had started with a less or equal to than an equals version. So now what I'm going to tell you, and you see it's like a very small modification. So it's not that different from what I just said, which is why I started with this one because it's just a bit easier to understand. But now I'll tell you what the version of forecast is for the inequality form, forecast in inequality version. So um, the main, I'll kind of like write well, I'll write what happens here, and then I'll kind of give like a bit brief explanation for why that occurs. So, but it's kind of maybe better to write the statement first, and then I'll give you the proof. Um, so like the only thing that I'm saying is that instead of having equals, now I have less or equal to b. Okay, and then I'm looking at x greater or equal to 0. Okay, so this is like the version, the way I'm going to write it down that I'm interested in, which is um, what if this doesn't have a solution, right? Okay. Well, actually, like I'll give an explanation because it's before telling you what happened. So, how is it that we dealt with these systems of inequalities with the simplex method? We would add slack variables, right? So, kind of like the way to turn inequalities into equalities is that you would add slack variables. So let's like add slack variables. So I'll write the vector now as like the new vector. I'll write f uh, like for forecast because it's like in the forecast lemma. So you would have like the original variables, but then you would add some extra variables which were these slack variables. So I'll just write s for slack. Oh, I'll write x sub s for slack. Right. So these were like the extra variables that you would have to add one for each inequality, right? And the idea is that when you added extra variables, right? I mean, I think we kind of like discussed this a lot previously, but let me just go back to one of the previous slides to kind of show you how that looked like. Where did we have? Let's see. Right, kind of like in the simplex method, whenever you added the slack variables, you would get like this copy of the identity matrix. That's kind of like the point because so this was almost always like for free, that happened. That's what made the method like useful. Whereas like in this other one, yeah, here like we have like 3, and then you have like the identity here, right? So the point of adding Slack variables is that it gives you like a copy of the identity matrix. So the matrix gets kind of like augmented, right? So like the matrix gets enlarged, right? And by that I just mean that you add the identity matrix to after A, right? And the point of doing that is that it would turn, it would turn the system of inequalities into an equation form, right? Right. So that's the main reason why we would use, why we would use like these as like variables to turn every inequality into an equality, right? So if this doesn't have a solution, right? If this doesn't have a solution, you end up in option two of, you know, so let's call this one and two, or let's call it A and B, actually, A and B. So like the way this trick works is that if the original system does not have a solution, then the new system with select variables wouldn't have a solution either. Like the solutions kind of like don't change. Like, it's just like a useful reinterpretation of then neither does P. But if this doesn't have a solution, right, we are in the second case of Farkas lemma because this is already like an inequality, right? So, but then option two in Farkas lemma, it says that, it's kind of like the picture that I had before, like the separation picture that you could separate the vector from the cone. It's just that this cone is made with the columns of AF. So this is like the cone made from the columns of the matrix AF. And here you have the vector Y. And then here you have the vector B. That okay? That makes everyone with me. But okay, but again, it's kind of like the same is happening. So if you do, and I'm now going to focus on like the dot product. So that means that if you do the dot product between A and Y, that should be non-negative, right? Here, A is any column from the augmented matrix. Okay, so now we're working with this enlarged matrix. So in particular, you could choose like the first column of the identity matrix. So you could choose like, for example, the first column of the identity. So choose A to be like, this vector, if you remember the notation from linear algebra, is called like the vector E1, which is one followed by a bunch of zeros, right? So what is the dot product between E1 and Y? What would that give you? I mean, that would just give you like the first entry of the vector y, right? Like, like that's the point of these canonical vectors, right? Like the basis vectors, like they just like read off the entries of the vectors. So that tells you the first entry would be greater or equal to zero. But there's nothing special about choosing the first column of the identity matrix. You could have chosen any column of the identity, and if you do the dot product, then you would end up finding that all the entries of y would be non-negative. So basically, what I'm trying to say But this works, so, but the same works, uh, if you choose, with E2 or E3 up to EM, because like it's an identity matrix. So what this tells you is that now you can assume that the entries of the normal vector are non-negative. So that's the whole difference. So we find that Y is non-negative. So compared, I'm about to write this more precisely, but compare, what I'm trying to say is that what I'm like, just to go back, in the case of an equation, you cannot say anything about the sign. You cannot say anything about the sign of this normal vector. But in the case of an inequality, the slack variables, kind of like what they allow you is to force the sign of the entries of each of the entries here to be non-negative. So like you kind of like get an extra condition. So like Farkas lemma version 2. So this is like how I want to rate it. So Farkas lemma, what it says is that if this system of inequalities has no solution, then there is a vector v, sorry, there's a vector y, which is greater or equal to 0, like in the sense that every entry is non-negative. So this is like what's new, which can be separated from like the columns of A. Okay. For which B can be which is a normal vector to the hyperplane, right? So which is which separates B from the columns of A. So it's kind of like the same picture that we had before, but the point is that now each of the entries, so nothing changes, like you can think of the same picture basically, but now the entries of the normal vector are non-negative. That's kind of like the new thing that you gain. Okay, that's kind of like the main difference. So you get like this extra condition basically. Makes sense, questions about that? Okay, so finally, why is that useful? So after much preamble, I'll tell you how is the forecast lemma related to the duality theorem. So let me remind you what the duality theorem says. So, and you'll see why this version is useful in a moment, once I give you, and again, I'll give you like a very quick idea of why it works the way it's supposed to work, because like I don't want to get too bogged down into the details, because otherwise it becomes like a very long proof. But so back to duality, and then I'll mention some mathematical applications of the duality stuff. And then next time I'll talk about this game theory stuff. So again, for context, you had the primal problem. That is kind of like that is like the original optimization problem that you were trying to solve. So this was a maximum. You were trying to find a maximum of a function, right? Where like the inequalities, where like the conditions were that AX is less or equal to B, right? And you want the variables to be non-negative, right? So this is like how we have always started writing our optimization problems. That's kind of like the standard format for the optimization problems. Then the dual, right? What did I say? The dual literally reverses kind of like the main roles. So the vector of coefficients gets replaced with the vector of constants. So, and the max becomes a mean. So you're looking for a mean between the dot product of B with the vector which is called Y. Okay. And then Y has to be non-negative, like these are like the dual variables, sometimes called. And the inequality system that it satisfies involves like the transpose of the matrix. So the inequality also gets reversed. So you get something like this. Is that okay? Is that making sense? So that is the original is the primal problem. The dual is D. Okay, so what we had mentioned before with weak duality. So what weak duality had said is that any value for this function is above the values that you get from the other function. So kind of like the dual is at least as high as the values of the primal. So like in a graph in in like in a picture, if you think, let's say that this is where the max happens for the primal problem. This is where the max of the primal problem occurs. And then you have like all these potential values, you know. So the maximum value for this function happens somewhere on the number line. What weak duality says is that the minimum, like, any value, any value here would be higher than all the values in red. So the values for the minimum, like, here, like, would be the min of the dual if they're finite numbers. Like I'm drawing the picture in the case that they are like finite numbers. So you know, any value that you get for this function with a vector y is higher than any value that you get for the original function with a vector x. Okay. But the strong duality, which is what I'm going to tell you about today, is that there's no gap in this picture. So the max and the mean coincide. Okay. So what the strong duality theorem says is that if each of these if each of these systems has a feasible solution, then there's a max and a mean, and the values of the two are the same. So but like in a picture, what it's like the strong duality says is that there's no gap. That's how you could summarize it. It's like a no gap result because it's saying that in this picture, like actually like true picture is something like this, where the max and the mean occur at the same point. So the max of the primal problem is the same as the mean of the dual. That's what I'm going to explain now in a moment. So yeah.
So
Uh-huh.
in the weak duality, like the max of P equal to the mean of D.
I mean, the thing is like
It's a subset of the strong duality.
right, like right, like like the weak dual, like that it's just like the weak duality is easier to prove. So, right, but the strong duality is actually like the duality that you care about. It's just like the weak duality is really like a 2-second proof, which we had done before. The strong duality, if you and again, like it is like a longer proof, so I'm just going to give you like an idea of how it works. but it uses the Farkas lemma. So you had to talk about first about Farkas, and I still haven't written the statement. What I was going to say is that what the strong duality says is that if each of these systems has like at least a feasible solution, then the max and the mean are finite and they are the same value. Okay, so but in the picture, that's how you should think about it. So. So what the strong duality says is that if the primal and the dual have feasible solutions, then there's a maximum, like the max is finite. So the max is finite and the mean is also finite. And moreover, those two numbers agree. So like again, if the max is finite, that means that the max occurs at some vector, which I'll call x max, because that's where the max would occur. And if the mean is finite, it means that it also occurs at some vector, which I'll call y mean. So here, like, this is like, like wherever the maximum is yielded, obtained, and also wherever the minimum is obtained. Okay. So again, I'll kind of give you like a brief idea of why it works. It's just like a very clever application of the Farkas lemma, so it's kind of worth just mentioning at least the basics of how it's supposed to go. The book does have like a does give like a very nice explanation of everything. So if you want to kind of go through all the details, you can read the book. But but the basics are kind of like easy to understand enough if you kind of know this Farkas lemma already. Um, And then I'll kind of give you some consequences of the duality theorem from like a mathematical point of view. And then next time, yeah, we'll do this game theory stuff. Um, so yeah, I think. Okay, so but is a statement making sense? Like it just says like the two numbers collapse, like the max and the mean agree, which is what makes it so nice. So, but here's like the main idea of how you would prove this. Um, So let's call like I don't know what the value of the maximum is, so let's call that M. So like big uppercase M for max. Okay. So I'll do something that has like a very much like a calculus flavor. Um, which is like simple idea. Imagine that the max is 10. If the max is value 10, then that means that like think about it as temperature, right? Like if the temperature is like the maximum value of the temperature is 10, then that means that there are no points where the temperature is 11, right? Does that make sense? So if the maximum value is M, there are no points where the value of the function is above m, because of that's what max means. Like, and these are really absolute max, so there's no complications of whether it's a local mean or a local max or something like that. So again, like the idea is that if the maximum happens at a number, above the number, there's no value, no points that attain that value, because otherwise the max would have occurred higher. So what that means is that this means there is no vector x for which c dot x is higher than m, right? Is that making sense? Because again, if there were like a vector with that property, then the max actually wasn't the max. That's what it means to be the max. You cannot find anything higher above it. Okay? That's kind of plausible. So like I'll just kind of make the, like the ceiling for like these dot products is like m. That's what I'm this is saying. But to be more precise, like these vectors are not at random. The vectors had to satisfy the being inside the polyhedron. They had to satisfy the system of inequalities. So what I'm really saying, so this is saying that, and I will kind of use like a more like a physics notation, that if you move a certain amount delta m, I'll throw in some deltas, that for any positive delta m, that making sense? So the first two, what are the first two conditions? They're just like the inequalities that if you think about it in the simplex method, the vectors are always inside the polyhedron. Like it's something we forget because once you have the simplex method, you can just work with the matrices. But ideally there was like this triangular region or like convex region, which is what we have called. We were looking for vectors that are inside the convex region that maximize the function. What we had said is that it happens at the corners of the polyhedron. But there was always like a polyhedron on the back of everything. So this is not, this is nothing like new. It's just saying that X is in the convex region, so that X belongs to the convex region and that it's feasible, right? Which is what we care about. What's kind of what I'm saying, like what I was saying a bit earlier, that was the previous paragraph, is that if you, again, like if you think of the temperature of the function being temperature, if the maximum temperature is 10 degrees, any amount slightly above 10 degrees cannot be found anywhere. Like, there won't be a point which is at 10.01 or 10.00001, because otherwise then the max would have been higher, So this is all that what this is saying, Uh, so this is like the previous paragraph, but kind of like written in a slightly more like calculus notation, because it's like a way of saying, if what makes a max is that if you increase by a tiny amount, there's no more like points where the function takes that value. That okay? Everyone with me? So far, so good? Okay. So if this is a system of inequalities, right, that has no solutions, this is almost Farkas, but we just have to reword it because, this is always less or equal. And the way I have this is, the way I have this is like the flipped. So I have to flip the inequality here, like move the so the variables always appear on the left-hand side. of the inequality, because like the way I wrote Farkas is with the way I wrote Farkas, all the variables are always less or equal to something. So, but it is a trick that we had talked before, because like it's kind of like multiplying both sides of the inequality by -1 essentially, and that flips the inequality. So that's not like a big thing. Is that okay? So again, like the only thing that I did was multiply by -1 the previous inequality to reverse it, so that all the variables like the x variable is always less or equal to n something, right? Okay, and then the next step, if you remember, I had said that one of the nice things is that you can write um, a dot product using the matrix multiplication. So if you want, you can rewrite this as in terms of the dot product. So you can say that this is the same as x greater or equal to 0, ax less or equal to b. And then what is a dot product? It's like the transpose times the vector. You transpose one of the first vector and then multiply by the second vector. Okay. So it's just like a nice, because then that way I can kind of like assemble these two into a single matrix, larger matrix, which is like A with minus C transpose. So, kind of like what I'll do. Is that okay? Is that making sense? So this is just like a new matrix. It's like the original matrix, but I just add like an extra row, like corresponding to this extra inequality. So this is like just a slightly bigger matrix than the one we had before. Let's call it AF for Farkas, because I'm about to apply the Farkas lemma to this. And this is exactly the same vector as before, but you added like an extra entry at the bottom for like the value of the max with some error term. So let's call this BF for Farkas. Okay. And now if you'll see that this looks exactly, now finally, this does look exactly the same the thing that I wrote earlier with Farkas lemma. It's just like I'm putting this F for like at the end of at the name of each vector. So this has no solution. Okay. Is that making sense? Okay, and so by Farkas lemma, if this has no solution, what does that mean? That means that this vector can be separated from the cone of the matrix, like of the cone of made by the columns of the matrix. So now we are in option 2 of Farkas. So we're in option 2 of Farkas says that you had the cone of the matrix, right? So this is the cone made by the columns of the matrix AF. Cone generated columns of AF. And then you had this normal vector, right? I'll call it n for a moment. You had this normal vector. You'll see why in a moment, why I'm going to call it n soon. And then you had this vector bf. Okay. Okay, so the thing that I don't want to explain here because that is like a little bit easier to get lost by is that what we do know is that and this is what I had said before in this inequality version of the lemma, right? What I mentioned before is that when you have the inequality version, you can assume that each entry of this vector is non-negative, right? Like that this vector is non-negative. What's a little bit like does take some extra time to argue in this particular case is that you can make the last entry of this vector equal to one. So it's a little bit better than just being non-negative. You can force the last entry to be one. Like that's not too bad to see, but like it's also a bit more technical than it kind of like would take us apart from like the main idea of like the proof. But it is in the book if you want to see that. So you know what you can do is that you can. So what I'm saying is that I can write this normal vector as a vector y, comma one. Well, it's actually like a column vector, I suppose. Like if you want to think about all of this as being column vectors. So, and this is what takes some extra care, but like again, it's in the book. So like, so you have to argue, I'll just make it as a remark. You have to argue that you can take the last entry of the normal vector to be one, okay? You can argue can be made equal to one. And remember here that y also recall that y is notice that y is greater or equal to 0 because we are in this inequality version of the lemma. Okay. And so here's like the magical part. So what is like the separation condition? The separation condition is that dot product between these two vectors should be negative, right? Like that's how we wrote the separation. So so and dot VF should be negative, right? But what is n? The way I'm expressing n is as y comma 1. And what is BF? BF was the vector b that the b from always, was the vector b with 1. Right? So they should be less than 0. Or sorry, did I put not 1, like minus m minus delta m. Sorry, oops. Make like the 1 is like in the other one. So it's b, and then this was the vector bf was this. Okay, so far so good. And this is really cool to see. So what is this dot product? This would be y dot v, right? Y dot v. And then you multiply the last two entries together, right? So you get minus 1. I mean, like that 1 doesn't make any difference. So you get minus m minus delta m. Should be less than 0, right? So it's annoying to put like have like all these like minuses. So let's move them to the other side. So that means that y dot v, right, is less than m plus delta m. Is that okay? That makes some making sense so far so good. So what that means is that like let's just try to see what's going on here. So you had the number line, right? M, again, what is M? M is the max of the primal, right? M is the max of C dot X. So this is where like the maximum is achieved for the original optimization problem. And what I'm saying is that if I move a tiny amount delta M, right? If I move a little bit to the right, I'll exaggerate it, so that I can write more easily. But if I move a tiny amount to the right, I can kind of like squeeze in a vector y where the value for this dot product is less than, less than that. So somewhere in here is located the value y dot v. Is that making sense? But what is y dot v? This is a function that you're trying to minimize in the dual. If you, sorry, just to go back for a second. This is like the function that you're minimizing in the dual. So what that's saying is that you can kind of like, no matter how big, so, but we were minimizing in the dual, we were minimizing y dot b precisely, right? So what happens if you start like shrinking this gap, right? If you take delta m to 0, it kind of like squeezes it to, it's kind of like a squeeze theorem kind of thing, you're squeezing the value of the mean. It's kind of very, I mean, it is really elegant, so it's like a cute proof. I mean, obviously there are a few details that I put under the rug, but like kind of like the main idea, like I'm giving to you right now, but it's kind of like nice to appreciate it. So take delta m, go to 0, and that forces like the values to agree. So take, and that makes the values equal. Okay, so this like Farkas thing really is like magical in a sense. Like it is like very, like you can give a very clever uses to get what you want. Has everyone taken here multivariable calculus? Okay, don't worry, don't worry. I was curious because I do want to explain a little bit of how this is related. I'll make a remark that will make sense for only those who have taken multivariable. But these variables y in the dual are like the Lagrange multipliers in multivariable calculus. I'll explain. I won't go into all the details since not everyone has taken multi, but it's kind of like good to at least put it out there like explicitly so that people know. So just as like a remark, like again, and before I say some more stuff, uh, the variables y roughly are the Lagrange multipliers if you consider like the optimization problem as a problem with constraints. Okay, y roughly correspond to the Lagrange multipliers. But what I will do is explain but I will kind of give you even if you haven't seen this, I will explain a little bit what's like the interpretation of the vector y. What does it tell you about the optimization problem? So I mean, there's a reason why we're talking about duality. It is because it's just like a convenient thing to have. Uh, so just if you do Calc 3. Okay, but still have 30 minutes. So another thing that's useful to like talk about first is also, okay, how to find the dual when you have the a system of equations. So until now, right? Uh, Let me just copy paste this recipe that we found. You know, like I'll just shrink this. Uh, until now, I told you how to find the dual of a system, right? Provided that system is defined with an inequality, right? If you had like ax less or equal to b. So until now, we have found the dual. We have found the dual of an optimization problem defined by inequalities, right? But like, sometimes like, and this happens in practice, sometimes like the optimization problem is just, I mean, the optimization problems can also be given just like with starting with equalities. There's nothing like, there are convenient, sometimes it's it is natural to have like inequalities, but sometimes like you do have like exact equalities. So you may want to find the dual of a system that like has equalities to begin with. Okay. So that's what I'm going to talk about now. Now we want to find the dual of something like this. You have a max where the vector is non-negative and ax equals b. So it's in equation form already. So one way to think about it is that maybe you added slack variables first. You added slack variables first. You get equalities, and you're like, okay, and then how do I find the dual after I added these slack variables, right? Like that's like a natural way to do it. But again, like even without adding slack variables, like equalities can appear. There's nothing against that. Okay, so the trick, is that you can think of an equality as two inequalities. Okay, and once you do that, then like it's not too bad to find. Okay, so the trick is that you can think. I'll write it first as numbers, right? You can think of, and then the matrix version is the same of ax equals b as ax less or equal to b and b less or equal to ax, right? So when you say the two numbers are the same, I mean, it's kind of dumb, but you say the two numbers are the same, you're saying that one is less or equal than the other and the other is less or equal, you know what I mean? Like the inequalities go both ways. Um, so, and that's useful because we do know how to find duals when there are inequalities. So what I'm going to do is to rewrite this system as a max of c dot a x of x greater or equal to 0, and then ax less or equal to b, and then b less or equal to ax. And again, these two conditions are the same as saying that ax equals b. Is that okay? Is everyone okay with? Okay, so we're almost there to take the dual, but again, to take the dual, you have to have all the variables less or equal. So again, I have to do like a similar trick to what I did a bit earlier. I will just multiply both sides of the inequality by -1 here to flip it so that I can put like the x on the other side. So I'll say that this is the same as max of c dot x where x is greater or equal to 0, ax is less or equal to b, and minus ax is less or equal to minus b. Right, so it's kind of like, imagine subtracting this and then subtracting the other, like just move them to the opposite sides. And now this looks better because you have like, inequality. Like it's now this have like, it has like more of a standard format. Is that okay? Is that making sense? Okay, and then I'll combine the last two inequalities. I mean, these are matrices and everything, but I'll combine these two into like a single larger matrix. So I'll write it as okay, this is like the final stage, which is why I'm changing the colors. So I'll write it as max of c dot x, x greater or equal to 0, and then a minus a times x is less or equal to b minus b. Right, like, so it's kind of like just like putting like the matrix A and below it, the matrix minus A. That means that every entry was multiplied by -1. And then you put the vector B and below it, the vector minus B. So that's how it would look like. That's how like the system of equations would get transformed into the system of inequalities. Is that okay? Is that making sense? Okay, and now this is ready. Now this is in a presentation where you can take the dual. So now let's take the dual, okay? And you'll see that something fun happens here. Okay. So what would be the dual of this? It would be, again, the max becomes a mean, right? Instead of putting the vector c, you have to put the vector of constants, right? But this vector in this particular case has like this particular shape where it's b negative b. So I'll write it that like that. And then you would have to do the dot product with y, right? Now, kind of, you'll see that in a moment. But because this is kind of like broken into two parts, I'll break the vector y into two parts as well, which I'll call y plus and y minus, because one is kind of like the one that's associated with the minus sign. So here I'll write y as y. There are a bunch of variables, so you can you can subdivide the variables. It's kind of like when we talk about like the old variables and the new variables after you add slacks, but it just like makes it easier to understand what the dot product would look like in this case. Let me put the plus or minuses at the bottom actually, because it looks a bit too messy. Okay. So that is the minimum of the function. And then what are the conditions on the vectors? The vector had to be greater or equal to 0, right? Meaning that each entry is non-negative. So each of these two pieces, like the entire vector, oh, sorry, I should have put plus minus here. So each of these separate pieces have to be non-negative. Okay. And then what was the condition? The condition is that the C gets moved uh, with B. So, and then you have to put the transpose. So you have to put the transpose of this matrix. The transpose of the matrix, but the matrix now has two pieces, A and negative A, times the vector Y. And the vector Y also has two pieces, which I'm calling Y plus and Y minus. Oh, you see something like very simple will happen soon, but I'm trying to give you like all the details so that you see where it comes from. Okay. But okay, so far so good. And let's just simplify this a little bit because it looks a bit too messy. So what is this equal to? This is equal to a mean of, okay, what is it, dot product? V dot y plus minus V dot y minus. Actually, let me call this vector y. I mean, like that's fine. That's I'll call it like that. And then what is a transpose? Like the transpose each is a transpose of each individual matrix, and then you kind of like turn like the column into a row. So it would look like this: A transpose minus A transpose times y plus y minus. Okay, so we're almost there. So you get what? You get the mean. So I don't know if you notice, like kind of like the vector b is present in both, so you can kind of factor it out. So you get b times y plus minus y minus. And then if you do something similar here, you get A transpose times Y plus minus A transpose times Y minus. So you can factor out the A transpose. So you would get A transpose. Is that making sense? So what do, like, well, the reason why I'm doing this is that what you notice is that when you take a dual, the only thing that that matters is kind of like the difference between these two vectors. The individual pieces don't ever show up. They only show up in as a difference. So what you can do is just, so when you take the dual, what you can do is define a new variable. So I'll call it yn for new, or d for difference and dual. Actually, that looks better. And and what you find is that what we just found is that if you had an original optimization problem where it was like this dot product where everything is non-negative and you had like this equation, if this was a primal, then what we just found is that the dual here, right, is a mean between this vector b and this vector yd that I'm calling now, where C is less or equal than A transpose YD, right? But what can you say about this vector? It is a difference, right? So even if both vectors are non-negative, like just think about it in terms of numbers. The difference of two positive numbers could be positive or could be zero or could be negative. So what happens is that when you take the dual in this way, there are there's no positivity condition on the vector. So you just get that yd is like some vector on Rm. So you cannot say, you no longer can say whether the vector is positive or negative, at least if you write it in this way. So like it is literally finding the dual for a system of equalities is the same. It is the same recipe. The only difference is that you lose the restriction. You no longer have the condition that the entries, the variables have to be non-negative. That's what I'm trying to say. I wanted to show this explicitly because otherwise it's hard to identify where that happens. But it's just like if you when you take the dual, you see that only differences show up, and that's where instead of having two variables, or like it's better to combine them into a single new variable. and regard the dual that way. Okay, so like let me write that in words. So the difference is that so the dual is found in the exact same way, found exactly as before, but you no longer have any conditions on the variables being non-negative. But you no longer ask for the variables to be non-negative. You no longer ask for the variables to be non-negative. So like just to like make an example, a quick example. So like say, like just to do like a 2 by 3 case. So, if I had asked you to find the max of these two things, like I don't know. Oh, actually, let me put three inequalities here. So you wanted x1 to be greater or equal to 0, x2 to be greater or equal to 0. And just to make sure like it makes sense, I'll put three inequalities. Oh yeah, kind of like in the farmer's problem. So that x1 is less or equal to 3, x2 less or equal to 4, let's say, and x1 plus x2 less or equal to 5. I believe that that's how we had written like the inequalities for the farmer problem or something along those lines. Uh, yes, I think so. Right. Yeah, so we have 3, 4, and then some point, right? Because right, 3 comma 4 would have been there. Yeah, 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 like that looks fine. Okay, so what is the dual? Oh, okay, but then I wanted them. This is so silly because I wanted to show you how this would look like with the equality. So yeah, yeah, yeah. So let me. So well, let me do one of each now that I do it like that. So if you had the primal in the inequality in the dual version where everything is with inequalities, right? Then it would become the mean, right? You take these coefficients, so 3, 4, 5, so it's 3y1 plus 4y2 plus 5 y3. Now you want each variable to be non-negative. And then the vector c is 1, 2. So that's a vector of coefficients. And then the matrix transpose, I'll just write it, it's 1, 0, 0, 1, 1, 1 transpose less than y1, y2, y3. Okay. That's how that would look like. I mean, of course, you can take the transpose to simplify it a little bit if you wanted to, because yeah, maybe this looks not super nice, but that's kind of like the basics of the dual. So these numbers 3, 4, 5 become 3, 4, 5 here, and then what I want to emphasize is that 1 and 2 become 1 and 2 here, right? And then you identify the matrix of coefficients A, and you transpose it, and that's how you get the dual. So this is like in the inequality format. If I had given you the already kind of like everything in equation form, right? So if I had given you something, let's just to put something like not too dumb. So if I had said like max of x1 plus x2 minus x3 plus x4, I don't know. But then like I'll give it, you know, they are all like non-negative. But then like let's say I give two hyperplanes, like that would give you something two-dimensional. So again, this could have come from after adding slack variables or whatever. I don't know, like or like maybe in this case there are no natural slack variables. It was just like a problem that happened to have like four variables, and that's it. So now this is like the equation form, right? So this is the primal. So what is the dual of this? So again, it becomes a mean. Oops. So it becomes 4y1 plus 5y2. And again, these numbers come from, I'll use the same colors. These numbers come from here and here. Okay. And then 1, 1, negative 1, 1. So the vector is, oops, the vector is 1, 1, negative 1, 1. So again, that is supposed to match here this, and this. Dun, 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 dun. Okay. And then you transpose that matrix. So the matrix would be 1, negative 2, 1, 1, 2, 1, 1, negative 1. All of these transpose, right? Times y1, y2. But you see, like the point here is that now I'm not asking for y1 and y2 to be negative, non-positive, non-negative. So here they're not, because I already started it with equality like as an equation. So here I'm no longer let me put that explicitly. So I'm no longer asking in this duo y1 greater or equal to 0 and y2 greater or equal to 0. That's the main difference between the two. So this is sometimes called the asymmetric version because it looks less symmetric than this one, right? Like if you start with the inequalities, everything looks a lot more symmetric. But like in practice, many times you just like if you have it already in equation format, then that's how it would go. Is that making sense? So when is our next exam, by the way? Is it like 2 weeks from? No, does anyone have the syllabus? I think definitely it's not that next week, but it may be Monday. Can anyone check the syllabus just quickly before that? I feel. When do I have it? Is it a Monday or a Wednesday? And 14. Okay, 14 would be a Monday. Now would it be would no the third exam? Yeah. Okay. I mean I have like kind of like the idea of like having it on Wednesday so that I can turn the Monday into kind of like a review day. So may I'll have to kind of send an announcement about that, but if it sounds good, maybe we could do it on the 16th instead, so that Monday I can do the same where it's just like feel free to come if you the thing because if like it doesn't make sense to have the review day next Wednesday because no one would have studied like it kind of buys some time for people to have kind of like at least 2 full weekends to go through the material. So what I'll do is I'll kind of send you tomorrow like a list of problems, kind of like the study guide for the exam. It will be only on duality stuff. So and then right we'll have 2 more classes on this duality stuff. So we'll be done with the material for the exam on Wednesday. And then Monday, I'll turn it into review day. And then Wednesday, I'll turn it into the actual exam. So I'll move it by 2 days. I think that's better so that you have more time to practice. And also that gives me some extra time to add some problems and set up some assignments. But yeah, my goal is to like the third exam will only be on duality. I may not even I'll have to think about it, but probably I won't even ask you to like do anything with the simplex method, like to solve anything explicitly with that, because that was already covered in exam 2, and the final is final. So like that's where like you would ask it again. So it's kind of like find a duo of this or like this Markov chain, identify the probability matrix. I have like most of the problems already ready, so I'll send them tomorrow. But let's leave it like that, and then I'll kind of send an announcement so that we can do it that way. And I'll move officially the date by 2 days then. Okay, good. I'm glad we talked about that. So let's end here. And then on Monday, so Monday, yeah, I'll just do more applications of duality. I'm more or less done with the theory, but yeah, there's two important things to say. So yeah, Monday and Wednesday will be the last 2 days of topic material for this. Yes. No, I'll probably, they will like I'll put something super short, but I'll make it due next week, next Wednesday, let's say. Yeah. But like, yeah, if you do it over the weekend, like for example, it would be like a problem of this, like find the duals or like very basic things like or like this Markov chain. identify the matrix from the graph and what would be the system by Farkas lemma that you would have to show doesn't have a solution or something like, like they won't be, definitely these problems won't be that computational. So it would be more like, do you know, like, yeah, so they won't be, yeah, but I'll definitely do it on Wednesday so that if someone wants to ask me about it on Monday, any of the questions you can. So yeah, but I'll definitely send the problems by tomorrow, and an assignment for people to work on. Yeah, yeah. But okay, good, good. Let's finish here, and I'll send you more info about that.